Hello everyone. We will continue studying absolute minimizing equation, and today we will talk about enjoys comparison with cons. Definition. We have U is open bounded domain. In Rn. A function U which is continuous in this U enjoys comparison from above in U. U is our domain. If for every compactly bounded subset of U and every cone whose vertex is not in V satisfies this inequality. U is less or equal than C on domain V. So after that we can conclude that U is less or equal than C in all V. What does it mean? For example, we have U, and every bounded enclosed domain inside it. We take our Cx was A plus B x minus x0. Now our x0 is not in V, so it's a little bit outside of this our domain, maybe here. Here is our x0. Now if this inequality whole cones like this, maybe this, or we choose another A, something like this, is greater than U on the boundary V, it means here. If this function is greater than our solution in the boundary, which our solution, for example, will be like this, that means that these cones will be greater than U inside of V. Here also this will be greater. Okay, we will again we will repeat it when we talk about infinity Laplace equation. So another definition, what does mean a function U which is continuous in our domain enjoy comparison with cone from below. Enjoy comparison with cone from below in U. If, only if, for every subdomain of U, which is bounded and closed and compact. Bounded closed means compact. And every C whose vertex x0 is not in V, it means x0 is in U but not in V. Satisfies this equation, U is greater or equal than C on the boundary. So we can conclude this, that U is greater or equal in with C in all V. Or in other words, if minus U is comparison with cone from above. Okay, let's prove one small lemma. The following conclusion is equivalent to U, which is continuous in U, enjoys comparison with cone from above in U. For every V which is compactly bounded in U and B which is from R and Z which is not in V, we have this inequality Ux minus Bx minus Z less or equal than the maximum when omega is on the boundary, U omega minus B omega minus Z for every X in V. How we will prove it? First we will prove necessity. Okay. Let V is compactly bounded in U and B is R and Z is not in V. Then we have Ux minus Bx minus Z then equal then maximum W minus B W minus Z when W is on the boundary of V for all X and V. We can write it like Ux less or equal than Bx minus Z plus maximum U omega minus B omega minus Z. We know that maximum of some function is one number. Maybe this one is A plus Bx minus Z. It becomes like cone. Because this number, A plus Bx minus Z, we know that this Z is not in V, so it is cone. So for con L-6 that is not contained, since we know that U is enjoys comparison from above, so we can conclude that x for all x in the V is true. Just we have to prove when x is in the boundary. When x is on the boundary, we get ux less or equal, then sorry. Because we said we assumed that we have enjoy comparison with cone above, then we can write it like this. So we have enjoy comparison. So it means we have this equation for all x in the B. So we can write like this, proved. If we have enjoy comparison, then we can write as ux less or equal a plus b x minus z. Now we have to prove sufficiency. It means if we have this inequality, we have to prove that we have enjoy comparison with cone. What we do? Let V is compactly bounded inside of U, and let Cx is equal to a plus b x minus z for a, b, r, and be any cone. This is like any cone which z is not on the V. So we have u less or equal than this according to the assumption on the boundary. Because we have this inequality everywhere, so we can conclude that we have this one in the boundary. Now we have to prove that it's true everywhere. So ux minus b x minus z less than equal to maximum u omega minus b omega minus z. Omega is in the boundary. Then we can write this as ux minus a minus b x minus z less or equal, then just a is one constant, then so when we subtract both sides from a, nothing will change. uw minus a minus b w minus z. So w is on the boundary. Now we know that this is our cone, any cone. Ux minus our cone x is less or equal than the maximum u omega minus cone with cone of w. So when w is on the boundary. Now, because this is cone on the boundary, and this is our u on the boundary, then we can conclude that this one is greater than this one. Because we had that for all x on the boundary, u omega is less than or equal than c omega. Therefore, this is less or equal than 0. So prove that ux minus cx less or equal than 0 for all x in V. So ux is less or equal than cx for all x in V. Now we proved that ux is less or equal than cx everywhere, so u is enjoys comparison with cone from above. But I have one question. What we did? We just, according to this lemma, we have enjoy comparison with cone from above. Then we can write this inequality. So, in other words, we have here for all x we have this, so we can say that this enjoy comparison with cone. Now in the sufficiency, just we wrote that we know that u is less or equal than c on the boundaries, then we can conclude that u is less or equal than cone everywhere. So the lemma proved. Okay, next lecture we will talk about connection between AML and comparison with cone.